So in this video, we're going to do an example for the finite quantum well, just so you can get a better sense of the differences between it and the infinite model. So let's say that the length of the quantum well, let's call that, well actually let's just call that L, is equal to 8 nanometers. The potential V naught is equal to 100 millielectron volts, and the electron mass is 0.06 times the mass of the electron in free space. And so if we draw out a diagram of what this looks like, this is V naught. So if this lower energy is E is equal to 0. And this is our length L. So this is 8 nanometers. And this V naught is equal to 100 millielectron volts. Okay, so first thing we should do, and let's say the first thing we want is calculate the infinite potential well energy. For the first energy level, or the ground state. And so this basically means that we don't care about the finite potential height. We just pretend that this 8 nanometer well has an infinite potential. And so we can calculate the first ground state. We have an equation for it. We know it's just h bar squared pi squared over 2m, and in this case, this is m of the electron times L squared. And if you haven't seen this electron mass or this effective mass before, in semiconductors, the electron mass or the apparent electron mass is actually tends to be much lower than the electron mass in free space. And I've gone over the reasons for that in other videos. But so if we plug in all the numbers, so we plug in Planck's constant and pi and the mass of the electron and the length of the quantum well, we'll get that the first energy level is about 98 millielectron volts. And so now we want to compare this to the finite well energy. Similarly, the finite well energy of the first state, or the ground state. And so how do we get started doing that? Well, I'm going to use the graphical method in this video, but you could also solve it numerically. And so the first thing to do in solving it graphically is we said that we had a couple of equations. We said we had y was equal to x times tangent of x, and x squared plus y squared was equal to r naught squared. And so all of the physics, like the potential, the length, the electron mass, all of that is wrapped into this single coefficient r naught, this unitless coefficient. And so that's the first thing we need to find. And then we need to find where these two curves intersect. So when these two curves are equal to each other, where they intersect, that's where we have a solution. And from there, we know that we can find the energy, because that's just the infinite well energy times x over pi over 2 squared. And I should make a note that this is just for the ground state. This is just for the ground state. And that was because to derive this, we had to multiply and divide by pi squared. And instead, we would multiply and divide by pi squared n squared. So this formula will need to be slightly modified if you use it for things that aren't the ground state. I think you just need to add an n squared in the bottom, or an n in the bottom. So the first order of business there then is figuring out this r naught. And in the previous video, we said that we could calculate it just from the definition, from setting it up. And I believe it was 2me L squared times V naught over h bar squared. Or sorry, that's actually 4h bar squared. And so if you plug in all the numbers, you'll get that r naught is about equal to 1.59. And so this is the radius of the circle. And this is actually just a little bit greater than pi over 2, which means that we're going to have not just the ground state, but also the second state available for our system. And so now we actually want to plot this. So if we plot this on a graph, And I plotted this in Mathematica to solve this problem, but you can use whatever plotting software you like. The plot should look roughly like this. We've got a circle, and this is of radius 1.59. And so this is the y-axis, this is the x-axis. And then that's intersecting this curve. This is y equals x times tangent of x. And it asymptotes way up here. And the intersection point, so this point is 1.59. The intersection point is at about 0.94. And so from this we can calculate the energy. And when I say 0.94, I mean the curves intersect at this point, but the x-coordinate is 0.94. The y-coordinate I actually don't care about because we don't need that to calculate the energy. And so if we plug in 0.94 into our equation above for the ground state energy, we'll get that it's, so our ground state energy for the infinite potential well was 98 MeV, and then divide that by 0.94 over pi over 2 squared, and we'll get an energy of about 35 millielectron volts. And so if we compare these two answers, so 35 millielectron volts was the answer for E1 we got with the finite potential well, and this is the more accurate result. So this is not the ideal infinite potential well, but our actual finite potential well, versus 98 millielectron volts for our infinite well. And this is less accurate. And you can see there's a pretty dramatic difference between these two. If I'm designing a device, I don't want to be off by a factor of 3 in choosing the energy that it's going to operate at. That's a significant difference. And so for small values of V naught, we're like V naught, say in the hundreds of millielectron volts, and typical quantum well values of around 10 nanometers. This difference starts to become really important. And so we do actually need the finite potential well model to calculate what the energy eigenstates are going to be, or the energy eigenvalues. And just to add the label over here, this is our curve x squared plus y squared equals r naught squared. So I hope you enjoyed the video. If you did, please like and subscribe below. And if you have any questions or comments, please post them also down below, and I'll see you next time. Thanks for watching.